Well, thank you all for coming. It is a pleasure to have Professor Carolina Araujo from IMPA give us a basic notion seminar on the Calabi problem.
Thank you, Alina. So thank you for the invitation. It's really a great pleasure to be here back at ICTP. So this is a basic notion seminar. So please, if you have any questions, interrupt me and ask me whenever you want. Okay, so I will tell you today about the Calabi problem. So before I start the math, let me introduce the mathematician. So this is Eugenio Calabi, who passed away a couple of years ago at the age of 100. And he left like a very important legacy in geometry. And in particular, this is what we are talking about today. He advertised this, became known as the Calabi problem in his ICM talk in 1954. And the goal of this seminar is to explain to you what the Calabi problem is. And so here is the problem itself. This is problem consists on determining which complex varieties admit a Kähler-Einstein metric. So I will explain all the terms in this question, but okay, this is the Calabi problem, and this is the plan for today's talk. So the Calabi problem comes, the existence of Kähler-Einstein metric is a problem that comes from differential geometry. And so the first part of the talk, I will just review some very basic notions from differential geometry. But there are some very deep connections with algebraic geometry. So I will spend the second part of the talk introducing some basic notions about algebraic geometry and in particular birational geometry, which is the field that I work on. And then finally, I will talk about the Calabi problem itself. And I should warn you that this is going to come from an algebraic geometry viewpoint. Okay, so let's start with differential geometry. And I need to tell you or remind you about the notion of curvature. So in geometry, this is probably the most basic notion. And let me start with the curvature of say a plane curve. So we can define the curvature as a measure of how much a curve deviates from being a straight line. And now let me give you more, a concrete way to understand the curvature of a curve. So we have a curve in the plane, and then we have a point P in the curve. We want to measure the curvature or define the curvature of the curve at this point. So what we do is we take the circle that best approximates the curve at this point P, and then this curve will have a certain radius r, and then the curvature is 1 over r. So if you have a straight line, this you can think of a circle with infinite radius, so the curvature would be 0, or say in this curve at this point here, this is the circle of the smallest radius that approximates the curve, so there it's the point where the curvature is bigger. So this is say a number, but also we have a sign convention. We want to put also add a sign to the curvature, and so we make some convention. For instance, in this case, we can say, well, if the circle that best approximates the curve is above the curve, then we say that the curvature is positive, and if it is below the curve, it is negative. So we have a number, but also with a sign. So this is a curvature for a plane curve. Now let's move on and talk about the Gaussian curvature of a surface. So let's assume we have a surface. For simplicity, we have a surface in R3, and now we want to measure, so let's see, So we want to measure the curvature of the surface or define the curvature of the surface at the point. So this is what we do. We take some plane that is normal to the surface at that point, and when you intersect the surface with that plane, you will get some curve. And then you measure the curvature of the curve the way I told you before. So you do this for all the planes that are perpendicular to the surface at that given point. And then you define the Gaussian curvature to be the product of the minimum curvature and the maximum curvature of the plane curves that you obtain this way. So this is the Gaussian curvature. And so this gives us a very known trichotomy. I call it like the great trichotomy of surface curvatures, which is here, the first one is a negative curvature. You see that you have in the saddle, you have the curves that it points in different directions. So the curvature is negative. The second one, curvature is 0. And in the third one, the curvature is positive. And one remark is that differently than the case of curvature of plane curves, the Gaussian curvature is something that is intrinsic to the surface. It does not depend on how the surface is embedded, say in R3, but only on the local geometry of the curve. And this is the Gauss celebrated egregium theorem. And to make this precise, I will recall some notions of Riemannian geometry. So how do we see these concepts in modern mathematics? Well, so first of all, in Riemannian geometry, we start with a Riemannian manifold that is a smooth manifold M together with a metric G. So a manifold is just given by charts, and then so open subsets that are identified with open subsets of, say, Rm. And then you have the transition function. So this is a smooth manifold. It's given by these charts. And the metric is it's an inner product at every tangent space that varies continuously when the point varies on the manifold. So this is what we call a Riemannian manifold. And once you have a Riemannian manifold, there is a way, this gives you a way to measure angles and distance. And then you can define curvature just from this information. And another thing that comes also from the Riemannian structure is what we call a parallel transport. So these are the notions that are going to be important for later on. So a parallel transport is just a way to move the vectors along a curve in a way that they remain parallel. So I'm just giving you a very informal definition. Okay, so let me finish this part by recalling a very important and classical theorem in differential geometry, which is the Gauss-Bonnet theorem. So the Gauss-Bonnet theorem relates the curvature of a surface with its underlying topology. So if you have a compact orientable surface, like this one, so topologically, it will be a sphere with a certain number of handles. This number of handles is what we call the genus of the surface. So in this case here, this surface has genus 2. And what the Gauss-Bonnet theorem says is that the average of the Gaussian curvature of S is just given by this formula. So it only depends on the genus, which is a topological invariant. And now, revisiting the great trichotomy for compact orientable surfaces in terms of the genus, so we had positive, 0, and negative curvature, that in terms of the genus gets translated into genus 0, genus 1, and genus greater or equal than 2. So this trichotomy manifests itself in many different ways. Here we're interested in terms of curvature. Okay, so now let me move to algebraic geometry. So I will tell you what are the objects that we study in algebraic geometry. So first of all, what is algebraic geometry? So this is the field of mathematics that studies geometric objects. So we're really interested in geometric properties of objects. But these objects are defined by polynomial equations. So polynomials carry a very strong algebraic structure that can be exploited to understand geometry. So usually we have this bridge that we want to understand geometry and exploit the algebraic structure, or vice versa. Say we want to solve equations and then maybe we cannot solve them explicitly, but we can, by looking at the geometric objects that they associate, we can get some qualitative information. We will see some examples very soon of this bridge. So now, what are the objects that we study? So let me first introduce the complex projective spaces. Actually, we can do algebraic geometry over other fields or even rings, but for this, because I'm interested in the Calabi problem, we will be working over the complex numbers. So the complex projective space is just a compactification of the affine space Cn, where we add 1 point for each tangent direction. So this is the complex projective space. And now let me introduce the complex projective variety. So Let me first start by, okay, as I said, they're defined by polynomials. So you take a finite set of polynomials, say in n variables, and then we can define what we call the affine variety, which is the points of the affine space Cn where all these polynomials vanish. So this will define some set in Cn, and then we compactify them inside a projective space, and this is what we call a projective variety. Let me give you a very simple example, plane curves. So a plane curve in a fine plane curve would be given by a polynomial of two variables in C2, and then we compactify them. So this will give you a curve, a projective curve or compact curve in CP2. Now, let me make I'm making here some underlying assumptions that this is a smooth curve, so that the derivatives of this polynomial don't vanish simultaneously at any point. So if it is smooth, in fact, this C can be viewed as a Riemann surface. You know, at every point, if the derivative is different than 0, we can use the implicit function theorem to write one variable in terms of the other. So this gives, so we can view C as a Riemann surface. And as a Riemann surface, it will have a genus, right? So, but now this curve was given by algebraic data, was given by a polynomial. And so we actually connect the algebraic and the algebra and the geometry. And in this case, yes, the genus of the curve, which we already saw that measures curvature, it's a topological invariant that measures curvature, can be completely computed in terms of the genus. So this is what we call the genus degree formula we learned in the first course in algebraic geometry. And so we see that algebraic information, the degree of the polynomial, translates into geometric information, namely the genus. Okay, now let's go to higher dimensions. And what I want to do now is to define the analog of the genus in higher dimensions. Now I have X, some complex projective variety defined inside some projective space. And what is the analogous of the genus in this case? Well, the genus, what we call the anti-canonical class, is just the first. So this is defined as the first Chern class of the tangent bundle. So if you don't know what the first Chern class of a vector bundle is, so don't worry. Let me tell you what you need to know. So this is an element of the second cohomology group of X, and what it does is, so if you give me a complex projective curve contained in X, then this curve will give me an element of the second homology group, and that means that I can compute the intersection between the anti-canonical class and the curve, and this should give me an integer. And what is this integer? This integer is nothing but up to a multiple, the average of the curvature of X along C. So again, this is what you should take it is, this is again a topological invariant, defined as a first Chern class of a tangent bundle. So it's a topological invariant that carries information about the curvature. We are going to re-encounter it later. Okay, now this canonical class or anti-canonical class plays a very important role in the problem, in the classification problem in algebraic geometry. So let me tell you what this is about. So what do we mean by classifying algebraic varieties? Okay, again, let's go to dimension 1. So in dimension 1, let me tell you how we classify varieties. So as we already saw, that given a smooth projective curve, then it has some genus associated to it. So we fix some discrete invariant, the genus, and then we put our curves in these boxes. So we classify them according to the genus. And now for every fixed genus, we have what we call a moduli space, which is an algebraic variety, an algebraic object that parameterize all the curves of genus G. So this is how the classification goes in dimension 1. In higher dimensions, however, there are way too many isomorphism classes, so we don't expect to have a classification like this. So the classification problem in higher dimensions is slightly different. And so we will not, first of all, we will not classify up to isomorphism. Instead, we will define a new notion of equivalence, and we will try to classify things with respect to this new notion. So let me start with an example, and then I will give you a definition. So this is a construction that appears in algebraic geometry all the time, which is the blow up. So the blow up. So I've illustrated here the blow up of the projective plane in one point. So what this is this is a projective variety that is obtained by. So here I have the P2, the plane, and it's obtained by replacing one point by a P1 of tangent direction. So here I have all this P1 of tangent directions through this point. And so in the blow up, I remove the point and I substitute it and I replace it with this whole P1 of tangent directions. We see what is important in this example is that if I remove the point from P1 and its inverse image in the blow up, what I have is an isomorphism. And so this gives me a very important notion of the notion of birational equivalence. Two projective varieties, X and Y, are projectively equivalent if they have dense open subsets that are isomorphic. And so, for instance, the P2 is isomorphic to its blow up in one point. And now, this is how we can describe the classification problem in higher dimensional algebraic geometry. So, in the first step, given a projective variety, we want to find a simplest representative in its birational class. So this is what we usually call the minimal model of X. And then once we know how to do this, the second step consists in construct and describe moduli spaces of minimal models with some fixed invariance. So today we will be more interested in the first step. And this is achieved by what we call the minimal model program. So this is a very important theory in higher dimensional algebraic geometry. So the goal of the minimal model program is, given a projective variety, to find a simplest representative in its birational class. So for instance, if you want to compare the P2 with its blow up, it's very easy to accept that the P2 is simplest than its blow up. Okay, so in dimension 1, there is not much to be done here because in dimension 1, birational equivalence is the same thing as isomorphism for smooth curves. So this was already done by Riemann in the 19th century. Now in dimension 2, this minimal model was achieved by the Italian school in the earlier 20th century. And basically, you only have to understand blow-ups. So if you give me a surface, so here we're in dimension 2, so if x0 is a given surface, then I will find the blow downs. I will find P1s that I can blow down to points, and eventually I reach a surface that cannot be blown down further, and this is what we call a minimal model. So this is very well understood. Now, in dimension 3, things get much more complicated, and then there was a few decades of work of many people, and then eventually I just cited Mori, but I mean actually a lot of mathematicians worked for here, but Mori was the one who completed the program in 1988, and that actually yields him the Fields Medal in 1990. So this was a very, very difficult a very challenging problem. And now in higher dimensions, the program is not completely finished, but a big advance was made by Birkar, Caccini, Haken, McKernan in 2010, and that gave us a minimal models for most important cases. So now we can say that we have a big chunk of the minimal model in any dimension, and as a consequence of the minimal model, every projective variety can be constructed from 3 classes. And so the canonical class here plays a very crucial role in the minimal model. And then after, so it usually does not have a well-defined sign. It's not positive, definite, negative, definite, or 0. And so every step of the minimal model, you try to make the canonical class more definite. And in the end, these are the 3 building blocks for projective varieties. So the ones with positive canonical class, which correspond to negative curvature, are the ones called canonically polarized varieties. canonical class 0, these are called Calabi-Yau type variety. And then I will explain to you why the name Calabi-Yau is given to these varieties. And then the case where the anti-canonical class is positive, so this would be canonical class negative or positive curvatures are called Fano varieties. So this is the observation I told you before. The sign of a canonical class is usually not well defined. Okay, so now I will finally get to the Calabi problem. Maybe it's a good time to stop and ask if there are some questions. Okay, if not, then let's move to the Calabi problem. So again, we want to understand which compact complex varieties admit a Kähler-Einstein metric. So now I want to explain these terms. And so first of all, what do I mean by a complex variety? Well, a complex, so I will explain first the Kähler condition. So what a complex variety means is just the same thing as a smooth manifold. But now, instead of having charts identifying open subsets with open subsets of Rm, now I use Cm. And in a way that the transition functions now should be biholomorphic. So this is what we call a complex manifold. So it's given by these charts. And now one way that we use to actually to grab this complex structure is the following. So this is often called the almost contract structure. So if you look at the tangent space at every point, we can look at the multiplication by I. And so this gives us a linear map in each tangent space whose square is minus the identity. So multiplication by minus y. And this is a way to capture this complex structure. And so we will use this J later on. Okay, so now we have a compact complex variety of dimension m. And then we capture the complex structure by looking at this linear map J. Now, let me define what I mean by a Kähler metric on X. There are many different ways of defining given the Kähler condition, and I will choose what I find the most geometric way to define what you mean for a complex variety to be Kähler. So you can always put a Riemannian metric on your given complex manifold. So now you see your complex manifold will be a real variety of dimension 2m. And so you can put a Riemannian structure, a Riemannian metric there, but it may or may not be compatible with the complex structure. So what do I mean by compatible with the complex structure? Well, first condition, I want the metric to be invariant by this complex structure J. So this is very natural. And now comes actually the interesting, important geometric condition. You also ask that this complex structure commutes with parallel transport. So this is one way of defining, I will give you another definition later on, but this is one way of defining a Kähler metric. It's a Riemannian metric on your complex manifold that is compatible with the complex structure. A note is that a compact complex variety may or may not admit a Kähler metric. And when it does admit a Kähler metric, it will admit an infinite dimensional space of Kähler metrics. Okay, so when a complex variety admits a Kähler metric, we call it a Kähler variety, Kähler manifold. And let me give you some examples. So the first of all is the complex projective space. This is what we call the Fubini-Studi metric. So it's actually, if you look in the text in books, this is actually a metric that is given in terms of equations, something very concrete, and then one check that it satisfies the Kähler condition. So CPN is a Kähler variety. And now if you have a complex projective variety inside some projective space, and you restrict the Fubini-Studi metric, again, you get a Kähler metric. So any algebraic variety is automatically Kähler. And for a Kähler variety, as I said, it may not admit, but if it admits a Kähler metric, it will have an infinite dimensional space, which I will call H of Kähler metrics. And then a natural question is, are there some canonical Kähler metrics on X? So if it admits an infinite dimensional space of metrics, is there some special metric that I can choose? Again, let's look at the example in dimension 1. So we have X, a compact Riemann surface, given again, this is the trichotomy in terms of the genus. If I want to write it in terms of the curvature, this is the trichotomy. And it turns out that given a compact Riemann surface, it admits a unique Kähler metric with constant Gauss curvature. So for instance, if I look at the torus, curvature is 0, you see the curvature is 0 in the sense that the average of the curvature in the torus is 0. But we see here clearly that there are points where the curvature is negative, and here points where the curvature is positive. So the curvature actually vanishes. But I can put a metric on this surface with constant curvature equals 0, and this is usually when we write the torus in this way. So in this model here, the curvature is actually, when we do this identifications, the curvature is 0. So this is the canonical metric in this case. Okay, so now we want to generalize this notion of a canonical metric to say higher dimension. So now I have a compact complex manifold. And now I want to redefine the Kähler condition in a way, or the Kähler metric in a way that it's more tractable. So remember, the Kähler metric is a Riemannian metric that is compatible with the complex structure. So now if you give me a Riemannian metric on X, I will define a real two form in this way. So it combines the metric G and the complex structure. So this is a real two, positive definite two form on X. And conversely, if you give me such a two form, I can recover the metric G. So it is equivalent to look at the metric and the two form. And in this language, the Kähler condition becomes very simple. It's just that you ask that d omega is 0, so that the form is closed. Okay, so this condition being Kähler is that this form, this just real 2-2 form is closed. And once this is a closed 2-2 form, it defines a element in the second cohomology group. So now I'm viewing this as a Véran cohomology. So it gives me a class there. Okay, so this class will be important. Let's skip it this way. But now let's look at curvature. Now I can define another two form on X, which is given by the Ricci curvature tensor. So starting with the Ricci curvature tensor, which is what I said that in higher dimension, we'll measure the curvature of your variety. It gives you a two form, so that is also closed. So again, it gives you an element of the second cohomology group. And then what is, the higher dimensional analog of the Gauss-Bonnet theorem is that no matter which class you start with, the Ricci two form is always the same, and it is nothing but the anticanonical class that I defined before. So this is, again, I said the anticanonical, the class measures curvature, and this is independent of the Kähler metric you start with. So omega could be different, could correspond to different classes, different cohomology classes, but the Ricci curvature two form is always the same, and it is it's a multiple of the anticanonical section. Okay, so now I will finally define what is a Kähler-Einstein metric. So first of all, we already seen the Kähler condition. So if you have a Kähler manifold, we can compute the Ricci curvature two form, and we say that a Kähler metric is Kähler-Einstein if the Ricci curvature two form is a constant multiple of the metric. And then we can renormalize to ask that this multiple is either -1, 0, or 1. Okay, so this is what a Kähler-Einstein metric is. And now the Calabi problem asks which compact Kähler manifolds admit Kähler-Einstein metric. So we clearly see a necessary condition. This formula here gives us a necessary condition, which is, well, we want that the curvature is a multiple of the metric, but the metric is positive definite. So this will tell us that the anti-canonical class or the canonical class needs to be positive definite. So this is a necessary condition. So, and then if you have a Kähler-Einstein metric, then it is essentially unique. So in this sense, it is canonical. Okay, so as I said, this formula here gives us the necessary condition for the existence of a Kähler-Einstein metric, namely that the canonical class has a well-defined sign. So a necessary condition for there being a Kähler-Einstein metric is that the canonical class is either positive or zero or negative. And this is exactly those three building blocks from algebraic geometry that we saw before: canonically polarized variety, Calabi-Yau type varieties, and Fano varieties. Okay, so let's look at the Calabi problem separately for these three classes of varieties. So the first theorem comes by Yau in 1976. He proves that for those Kähler varieties with the zero canonical class, then it always admits a Kähler-Einstein matrix. And now these manifolds are now known as Calabi-Yau manifolds for this reason. And then shortly after, independently, Aubin and Yau proved that for canonical class positive, that is negative curvature, again, we will always get a Kähler-Einstein metric. And now what about Fano varieties? And then things get much more complicated and much more interesting. So for Fano varieties, there may or may not exist a Kähler-Einstein metric. So the first obstruction was observed later, early on by Matsushima. So Matsushima observed that if a Fano variety admits a Kähler-Einstein metric, then its automorphism group must be reductive. So if you don't know what this means, let me just give you an example and a non-example to keep in mind. So if you look at, let's look at GA and GM. So GA is just the group given by the complex numbers with addition, and GM is just the invertible complex numbers with multiplication. So this is reductive, and this is non-reductive. So the precise definition comes from related to representation theory, but maybe having these examples in mind is enough for this talk. Because now I can give you examples. So here again, Calabi problem. Now we already saw it for canonical class positive and zero. So now for me, the Calabi problem is about Fano varieties, and we want to understand which Fano varieties admit Kähler-Einstein metric. Some examples, again, CPN, the projective space. Again, the Fubini-Studi metric is already Kähler-Einstein. And in fact, any rational homogeneous space is also Kähler-Einstein. Now, some known examples, Fanos without Kähler-Einstein metrics, and then we will use Matsushima's criterion, and we can look at the blow up of P2 in 1 point and in 2 points. So I explained you already what the blow up is, and for blow ups of the plane, they are very well understood. And see, this is their automorphism group is also well understood. And see, the automorphism group in both cases, it contains a term here with a GA, which is non-reductive. So for these two surfaces, the automorphism group is non-reductive, and therefore they do not have a Kähler-Einstein metric. And maybe this is a good moment for me to tell you about the classification of Fano varieties. So when we study Fano varieties, if you fix a dimension, there is a finite number of deformation families of Fanos in that dimension. So in dimension 2 for surfaces, here are all the Fano surfaces, which are usually called Del Pezzo surfaces. You can have CP2, the projective plane, you can have P1 cross P1, and the blow up of P2 in at most 8 points in general position. So these are all the Fano surfaces or Del Pezzo surfaces. Their automorphism group is very well understood. In particular, these ones, the blow up in 1 point and 2 points, are the only ones with a non-reductive automorphism group. So all the other ones have reductive automorphism group. And a very important theorem by Tian and Yau in the 80s and early 90s that gives you a classification of Fano surfaces that admit Kähler-Einstein metric. Basically, they prove that, so this 2 cannot have Kähler-Einstein metric by Matsushima, and all the other surfaces are Kähler-Einstein. And this was actually very difficult. I mean, I wrote it this way, but these were several papers. This is for each of the Fano surfaces. They studied the problem, and so the last paper is a paper of Tian in 1990, Invention is of 78 pages. So this is really, really hard stuff. And so you could think that, okay, maybe what about threefolds? So I gave you a list in dimension 2, and actually I could give you a list also in dimension 3. So in the works of Skovsky and Mori-Mukai, they classified all the Fano threefolds, and there are 105 deformation families. So there is a list, and there is actually a table. If you're interested, you could search for phanography. So if you go to phanography is it's a website where they give you a list of the 105 Fanos and gives you, their names and address, and everything you want to know about each one of them. So they're quite well understood, and probably at that time it would be something unimaginable to actually solve the Calabi problem for these manifolds. And okay, so let's restrict to this case here. Can we determine which one of the three-dimensional Fano varieties admit a Kähler-Einstein metric? And just a remark to see how complicated things get starting in dimension 3. There are some of this deformation family that simultaneously contain members that admit Kähler-Einstein metric and members that don't admit Kähler-Einstein metric. So this is something that we did not see in the surface case, but already starting in dimension 3 starts to appear.
So
yes.
Sorry, you mean that this deformation process, the fact that having a Kähler metric is not stable under this deformation?
No, it's not. It's very subtle.
These two things are not compatible with each other. I mean, okay. But this starts to happen in dimension 3.
It starts to happen in dimension 3. Okay, so before let me just discuss some analytic tools before I want to tell you about the algebraic geometry tools, but let me discuss some analytic tools. And those actually I have to say that I learned here at ICTP when I spent a few months here in 2019. Claudia organized a working group on Kähler-Einstein, and then I learned many of these things back then. So if you have a Kähler manifold, let's fix X, and now I'm fixing, instead of the metric G, I'm fixing the 2 form omega. Then, as I told you before, that there is an infinite dimensional space of Kähler-Einstein metric. So this is how one usually writes this space. It's called the space of Kähler potentials. So this is giving you all the metrics in the same cohomology class, all the Kähler metrics in the same cohomology class of the one you started with. And this is an infinite dimensional space. You can put even, you can put some structure. It's a homogeneous space, a hyperbolic infinite dimensional space. And now a Kähler-Einstein metric would be some point in this space. And then this is one way that you analytically can make sense of this Kähler-Einstein metric. You define what we call a Mabuchi functional, an energy functional in this space of Kähler potentials. And the Kähler-Einstein metric corresponds to a minimizer for this Mabuchi function. So maybe this is what we need to know from the analytic side. And now I'm going to move to algebraic geometry, but I want to keep some. I want to keep a bridge with this. So let me just keep here this H. So this is the space of Kähler potentials in a given Kähler class. And now comes the notion, very technical, I have to apologize, but okay, this is what we have from algebraic geometry, which is called the K polystability. So let me define you what K polystability is and trying to keep a connection with analysis. Okay, so first of all, we start with the Fano variety for which we want to solve the Calabi problem. And then I will define what we call a test configuration on X, so for X. So it is a test configuration for X. This is, first of all, it's a family parametrized by the affine line such that the general fiber outside of S, the fiber is isomorphic to our given Fano variety X, but then over 0, I allow some degeneration. So, and here I put a singular point because I really allow this degeneration to be singular. If you have many components, it could be a mess. But the important thing is that this is an algebraic family whose general fiber is always X, and that the special fiber, it will be anything. And moreover, there is one more data to a test configuration, which is a C star or GM action. So I have a natural GM action on A1, which gives me by just the reparametrization of multiplying by lambda. And then I want an action, a C star action on X, such that everything here is equivariant. So this is the information of a test configuration. Now, let's see how it relates to this space of Kähler potentials. So this is the total space of the family. So over each point I have X, and then the total family is what I call this calligraphical X. So my X here would be our given Fano variety X. Okay, so now suppose we have a test configuration. If you can embed this, there's an extra data that allows us to embed this in some projective space. So if I embed them in a projective space, so let's say for t time 1, I embed it in a projective space, and then on the projective space, I can restrict the Fubini-Studi metric, and this will give me a certain point for t equals 1. This will give me a certain point in the space of Kähler potentials. Now, if I embed this family, this whole family, if I embed it as a family, and I pull back the Fubini-Studi metric for each t different than 0, what it gives me is a ray, in fact, a geodesic ray in this space of Kähler potentials. This is corresponding to this test configuration. Well, not any ray, but sort of an algebraic way, because this an algebraic ray, because this family here is algebraic. It's assumed to be algebraic. And now one defines the Donaldson-Futaki invariant, and the way that it was originally defined by Tian is in terms of weights of this action, and then later Donaldson reinterpreted as a product of cohomology classes. So this is I'm not writing the definition, it's not necessary, but I just want to tell you what it is. So this is going to be a rational number, and what it is the following. If I have this ray and I look at the limit of the derivative of the Mabuchi functional along this ray, this is exactly this Donaldson-Futaki invariant. So this is, let me just say it again, this is the limit of the derivative of the Mabuchi functional along this ray when t goes to 0. And so therefore, if you want your Fano variety to admit a Kähler-Einstein metric, the Mabuchi functional should have a minimum, and then therefore the Mabuchi functional, the Donaldson-Futaki invariant, has to be greater or equal than 0. If you want a minimum, the derivative at infinity cannot be negative, right? So otherwise you would not have a minimal. And so this is sort of an easy implication, or at least a natural implication. And then the big conjecture, so let me define, okay, before I give the conjecture, let me define K-Pauli stability. So a Fano variety is K-Pauli stable if for every non-trivial test configuration, the Donaldson-Futaki invariant is non-negative, and it is zero if and only if the special fiber is also isomorphic to X. Okay, so if X admits a Kähler-Einstein metric, it will be K-Pauli stable. So this direction is sort of natural. And what was the big conjecture for many years is the converse. So this was called the Yau-Tian-Donaldson conjecture that says that if X admits a Kähler-Einstein metric, if and only if X is polystable. So what this is saying is the existence of a Kähler-Einstein metric, which is an analytic condition by nature, is equivalent to an algebraic condition. And this is now a theorem. So this was proved by, Chen, Donaldson, Sun, and then also there's work of Tian from 2015. They actually now, so now this is a theorem. Existence of Kähler-Einstein metric is equivalent to K-Pauli stability. So see, this was about 10 years ago. And then algebraic geometers started to work with this notion of K-Pauli stability. And there was an immense amount of mathematics that was developed in this last 10 years. So I'm going to just jump to the final statement. But what I'm not telling you here is a lot. So algebraic geometers, in particular birational geometers, started to look at this notion. Soon it became clear that the minimal model program is deeply related to this notion of K-stability. So works of Birkar have been used to give algebraic criteria for K-stability. But I'm definitely not telling you anything about this. But let me tell you something that happened in 2000 and in 2020. So there was this workshop in AIM, which was called K-stability and related topics, where people got together to discuss K-stability. And then in the morning, there were talks. In the afternoon, there were research groups where people tried to work on specific problems. And then I joined a working group that decided to look at the problem of K-Pauli stability, or existence of Kähler-Einstein metric for Fano threefolds. So we understood that there were enough tools that had been developed from the algebraic side that made it tractable to actually look at the Calabi problem for three-dimensional Fano varieties. And so this is the group, the Fano team. So it's myself, Ana Maria Castrevet, Ivan Chelstov, Kento Fujita, Anne-Sophie Kalogiros, Jesus Martinez Garcia, Konstantin Shremor, Hendrik Soes, and Nivedita Viswanathan. So when we started there to work at this problem, and then we worked for 1 year during the first year of the pandemic. We worked very hard and we actually proved our main theorem, which is for each of the 105 deformation families of three-dimensional Fano varieties, we determined whether or not the general member admits a Kähler-Einstein metric. So here is the summary. For 78 families, the general member admits a Kähler-Einstein metric, and for 27 families, no member admits a Kähler-Einstein metric. Of course, in the first case, there is a more refined problem, which is understanding which ones in that family admit the Kähler-Einstein metric and which don't. And many of the families we know everything, but there are a few families that we don't yet know exactly which ones are Kähler-Einstein and which ones are not. I should also mention that we did not have to do the 105 families because previously 65 cases were already known. And what I mean they were already known is because they fell into some general criteria. For instance, if you have a product, the product is Kähler-Einstein if and only if each factor is Kähler-Einstein. Or for instance, toric varieties, there are among this 105, there are 18 that are toric. And for toric variety, as usual, you have a combinatorial characterization of Fano variety? Well, there is some polytope, and then the origin is exactly the barycenter of the polytope. So many cases were already known. Was the work of Claudio on finite covers. So many cases we could apply previously known criteria, but there were 40 that we had to work, and it was like really one by one. And we were using the new techniques that had been developed, which I'm not telling you about. But in the end, we finished, and this was not possible to publish a paper with this result. So we actually published a book. So this was the book that was an outcome of this project, the Calabi problem for Fano threefolds. And I guess this is what I wanted to tell you today. So thank you. Grazie.
Any questions?
So can you tell us a little bit more about the deformation process and why it does not talk completely with the existence of Kähler-Einstein metric? Understand correctly? This is not.
Yeah, this is not, yes. So as I'm glad that I said that I'm going to say things from the algebraic perspective. So I have to say that from the analytic perspective, I do not understand it much, but it turns out that from the algebraic perspective, we have this notion of moduli spaces that we love so much in algebraic geometry. And for Fano varieties, in general, it's not, you don't have a nice moduli space. For instance, you could have a family. Let me see if I remember one easy example. You could have a family for which all the fibers except over 0, they are Fano, the same Fano, but over the origin, it's a different Fano or something different. So this cannot live in a moduli space because this moduli space would not be separate. I mean, you can have a family that has different limits. And it turns out that and this, in a sense, this is related, right? Because you could see one as a deformation of the other. And so what happens is that this polystability is exactly the condition that you need to have a moduli space. So the central fiber that you would get in the middle should not be in your moduli space. So if you only consider K polystable Fanos, then this is a more recent theorem, they actually fit in a nice moduli space, meaning that that deformation is actually allowed in algebraic geometry. So in a sense, these things are connected, but now how to interpret this from the analytical point of view, I would not. But one thing that one easy instance of that is using Matsushima's obstruction. So there are some of these families for which for the general member, the automorphism group is finite and reductive, but for a special member, it will be, say, something that has GA. So this is easy to construct. And so you see that it cannot have a Kähler-Einstein metric in this non-reductive case. So this is not preserved, unfortunately. But that's life, I guess.
Sorry, the general member, what do you mean, like specifically?
I mean that each one of these deformation families, they will have they have a certain description. For instance, they are the blow up of P3 at some points, and then there's some description. And then general means, for instance, if they come from the blow up of P3 in 7 points, then the 7 points have to be chosen generically. So if you choose them special, then it may fail.
So so you reference these many algebraic geometry techniques and developments of the past 10 years. So do those involve translating this notion of K polystability, relating it to the geometric invariant theory, for example?
So it seems that it's more complicated. Some people have been doing this, as a fun game. For instance, you look at cubics in Pn. So these are funnels. And then for cubics or hypersurfaces in general, you have a GIT theory. So for three-folds, the GIT stability coincides with the K-poly stability, but already for quartics, it does not. So it seems to be more subtle than geometric invariant theory.
Can you tell us a bit more about, like, so there was this K-poly stability, which was about test configurations and rays, and the problem of finding a minimizer for the function, right? So, like, can you tell us a bit more about the space? Because I just want to imagine what kind of rays, with what space, like what would be the issue there, like find the equivalence.
You mean here?
Yeah.
Okay, so as I said, these rays here that come from test configuration are very special, right? I mean, this is an infinite dimensional space, so most rays do not come from test configuration. And this is what is so impressive about this result, because it tells you that you only need to look at, say, geodesics in algebraic directions in your space. But I have to say that for this space, you have to ask Claude. I cannot tell you much. But I have to say, but maybe what I can say is a little bit about the techniques. So this is not what we do, right? We don't do test configurations in when we prove one result like this. We don't really look at test configurations. Now, in this last 10 years, that have been, for instance, invariants that one defines. That gives you, say, either positive or negative criteria. So, for instance, there's the alpha invariant, the beta invariant, the delta invariant. So these are invariants that are defined in terms of algebraic geometry and tools from the minimal model program that somehow capture the existence. So if you, for instance, one of the invariants that we use is defined in terms of exceptional divisors over some blow up or some model of your variety. So and then we define a beta invariant for that. And if the beta invariant is negative, there's no Kähler-Einstein metric. So how do we translate it? From if you find such a divisor for which the beta invariant is negative, you can associate a test configuration that is going to give you something negative. So we don't use this directly, but we actually use algebraic geometric invariants that are built to understand this notion. But as I said, I did not tell you anything about this.
Any further questions for me? Thank you very much again.
Do you get to talk to the students, I believe?
Are we?
Is there a closed session between Carolina and the students now after the basic notion seminar, or no?
We can decide. Is Carolina willing to stay 10 minutes?
Sure. I'm also here until the end of the month, so feel free. I'm in room 122, so you can also feel free to stop by.
So we wait for 10 minutes for you in the cockpit.
Okay.
In the back.
Okay.
Should maybe
students can
stop the recording.
probably. Yeah, we stopped the recording actually.
Students are free to ask questions.
Sorry. Okay, this.
Era el momento.
Okay.